employee display data coming from the base class. Now, the derived class temp from employee, as you can see, again, it has default values, and for the constructor, the way to design the constructor is by invoking the base class constructor. This was what was presented in the lectures. It was the way to deal with setting IRD, which is a private data member. Because we have in the class employee a set IRD, it was possible to eventually work with that public data, public method of the class. So there is set IRD, allows derived classes to work, but the best way is to use this approach with using the constructor with initializer list. So this is the derived class in which we override, print, and get net monthly pay. It's good to put that there to let the reader of the code know that these are defined in the base class for the first time. Your code will work without that, but this will be kind of part of the good style approach. And then, except for this print method, as you can see, in the employee class, the way to access information from the base class is just invoking the base class print method. And we have seen example in the lectures like this and in the code. This temp is a concrete class. Get net monthly pay, as you will see, is overridden. The formula to compute it is just based on what was explained there. The only bit is that we have to move from integer values to float values because we want the real number of hourly worked total pay for this employee. So it was not some complicated expression. Some people had trouble with coming up with this kind of formula. It was just addition, subtraction, and arithmetic of low-level thing. Salary employee, it was an abstract class because as we don't implement get monthly pay, it stays abstract, but we do some declaration for methods which are used in derived classes. Get annual pay, for example, is defined there, but is used in some derived classes from salary employee to compute. As you can see, for the administrator type object, we need to get the annual pay divided by 12 and get annual pay is, as you can see, not declared in the admin class, but it comes from salary employee class. And then we have a formula very similar to what we have seen before. I have decided to have print for salary employee just to be able to pass data from the employee class via salary employee to its derived classes. And then for professor, I designed two data members, MTex and days leave, and in order to compute its net monthly pay, I have declare some variables with good name, compute monthly wage, day wage, deduction for leave, and then I compute gross wage, which is monthly wage minus deduction for leave, and then I take into consideration the tax and return that value. For printing, again, base class for professor, prof class, plus information about the new data. So many things are, in a sense, quite repetitive. And hopefully you have got the idea. Yes?
Destructors? We had to write a destructor for the employee class?
For the employee class, what is this?
We had to write a destructor. Was there one? In your assignment, we had to write a destructor for at least the employee class.
You write a structure?
Destructor.
I see. Yes. If you put it, yeah, I forgot about it. You can edit, it doesn't do anything. Nothing. In some, yeah. It's virtual because of the, yeah, so you edit here and just empty brackets to practice with the syntax somehow. In the past, it was some warning that we have derived classes and they required call to their destructor. But apparently they fixed the problem. Any other questions? So that virtual destructor does nothing, just empty brackets, just to make some compilers happy.
Yeah, without the destructor, I was getting an error message.
Yes.
Might not work.
But I think now, with some other compilers, they have fixed the problem. They recognize it's not memory allocated in these cases. In some other cases, it's important. So you lose nothing if you make the destructor virtual, and it's a good approach. Okay, right. So this was assignment 2 part 1, and now we are going, okay, I have opened it already. Yeah. We have started talking about standard template library, and we looked at iterators. And I mentioned that there are 2 issues about iterators. One is the hierarchy of iterators, which is not an object-oriented hierarchy. We have input iterators, output iterators, okay? Forward iterators, bidirectional iterators, and random iterators. These are categories, and they are there to specify what operations are provided by classes of iterators as provided by various containers, what operations they should provide in order for various algorithms, which we will talk next, to work on those iterators. Okay, so one is the notions of iterators category, and the other one is the classes of iterators as implemented by various containers. And on top of that, we will see that there are constant iterators, reverse iterators. We are briefly looking at the constant iterators. Once again, they are there to make some tasks work on constant containers. If you have a constant vector, a normal iterator does not work. If you want a vector, it's constant, you initialize it to some values, and then you just want to look at display data in that vector. Going with an input iterator through the vector does not work. The iterator has to be constant. In other words, to promise that it doesn't try to change data in the vector, which was constant. The compiler check. My data is constant, then I don't accept anything except constant iterators. And there are constant iterators and reverse constant iterators. So constant correctness is a big issue in C++. Reverse iterators, we are not talking because we are not practicing with them, so just I remove that topic. And at the end, a little bit about loops for ranges and iterators. So, we have covered input and output iterator. We have seen that iStream iterator is providing plus plus and dereferencing. This is the set of features for an input iterator. This dereferencing accepts values when we use it. Output iterator, on the other hand, it's designed to go forward only and just to not change data, display. It's a output thing. Okay, so this we have seen how to initialize these iterators with standard variables. Up on the hierarchy, we have the forward iterators, which can do input and output, but again, it moves only in one direction, as you can see, plus plus. And dereferencing, you can read data which is here, you can write data which is dereference. So it's providing a little bit more power. On top of that, we can compare, which was not compare and assign between forward iterators, and these operators were not available in the input and output iterator. Okay. Bidirectional are coming with all operations for forward plus the option, the power to move backward one location. Okay. Now, the most powerful is this type of random access iterators. They come with everything which was in bidirectional, so everything which was in input, output, forward, plus this random access. We can jump n location. This is pointer arithmetic as you know it from C. Iterator plus n, symmetric n plus iterator, and you can move both forward and backward, jumping n locations. No other iterator has these powerful operators, and because it has this, then it comes with subtraction, it comes with all type of comparisons. It's important to notice that containers come with different type of iterators, and because they provide specific type of iterators, algorithm we'll talk next, will work on some of these containers and it won't work on the other containers. For example, vector double-ended Q are the most powerful. Sort global algorithm requires a random access. Therefore, to sort, you have to have either a vector element or a double-ended Q. You can't sort on a list or on a set because these containers do not provide the correct type of iterator. For associative containers, we know that they are already sorted, so sorting it doesn't make much sense. But for list, if you want to sort a list, be aware list comes with a method sort, which is efficient for this type of object. So when you have for some containers to choose between global function, which can be applied, it's not the case here, but assume that you might have find, which is sometimes provide for lists and for global algorithm. Preferable is to use the method of the container because it's designed for efficiency. The global algorithm is designed to work in various circumstances. It might not be the most efficient. But if you can choose between find global algorithm and find a method of a list, prefer method of a list and work with a list, hopefully. So this is the thing. As I said, only 2 containers provide random access. Then we have these bidirectional iterators for all other 5 types. Be aware, container adapters are not designed to jump in the middle of a queue or to jump in the middle of the stack. They have to work only with specific locations, stack only through the top. So it doesn't make sense to have iterators. Even if they are based on vectors, so the iterators are made private probably for these stacks in order to disallow them. Therefore, you have to know this in order to use the algorithm we will talk. Containers and iterators. Each container, every type of container we have seen, provide begin and end. Even the container adapter, better not use them, but they come with begin and end method which return iterator, so they have to be dereferenced. End is never dereferenced because points the one after the last significant. For some containers we have method to access references of objects front and back. So you should know this in order to work with them. Working with iterators make your code general and easy to use for different types. So we decouple the specific data structure used from the task at hand. And we have an example, and we go from the most specific to general thing. To compute the mean value of a set of data. Assume that we have a vector of floats. How the mean is computed, you compute the sum with this for loop, right? The sum will be stored in U, and we go with a for loop to update U every time, and then we divide the sum by the number of elements and we return the average or the mean, all right? And this is a task which can be performed with various numeric types and various collection of numeric types. In this example, we restrict our code to only vectors, right? If we want to move from array notation to use iterators, because sometimes you might have lists which do not have array notation. The way to adapt this approach is using a while loop, the best way. And you should note that it's quite repetitive in some sense. The sum of elements in the container is u, and we initialize it to 0, and then we keep track of how many elements we have read with n, and initialize to 0, and then we enter the while loop. IT is starting location, and this en will be the end. With this algorithm, we can compute the average of a whole set of elements, or we can compute the average of a subset, depending on where we start the beginning of the sequence and where we set up the beginning and end. So one generality is added somehow compared to the previous one, where we use the whole set to compute the average. And as you can see here, we go through each element, start this and compare against the end with not equal. Like we have seen previously, this is a typical way most algorithms are defined when working with iterators. And we update u with the value to which it points, and then we move to the next location and we increment the number of elements read, because this is a value which has to be updated. So at the end of this while loop, when it becomes equal to n, we have in u the sum divided by n and return. So as you can see, these are very similar. The thing is, when working with iterators, and we want to do be able to work with a whole container. When we work with whole container, size is known, but we want to work with part of the container, and then size is not known. And now we can compute the mean of any vector we can design, no matter what the size of the vector, just invoking our function with, in this case, the whole vector, or we can being a vector, say v begin till v begin plus 5 instead of the whole elements. But we would like to move from vectors to lists to double-ended queue to other containers, providing what operation is needed in this task. As you can see, one operation on top of dereferencing, just moving forward. This is the only operator needed for the iterator we are using there, right? Most iterators are dereferenceable, so this is common to all iterators. But the one which tells us how can we generalize this for what type of containers, we look at what operations are used for iterators, and we see that it's just reading data and moving to the next element. And this is output iterator. Read data which is there, sorry, yeah, look at the value. We don't change in any way that value. So this is read-only data. And then we move to the next location. Okay. But of course, elements have to be edible. Elements in the container has to be edible, like with plus. That's why we need it only for numerical types. And now, in order to generalize it, all we can do is, okay, we design a template type method, function, not method because it's a global function, and we have it as this iterator is for the reader of the class. It's not a specific type in C++. Be aware, my iterator type, you can call it whatever, type name or class, and you give it here a name. The only condition for that name will be to be able to move through each element forward and read the data in that location. So our function will work for all iterators which are output iterators, because we need values there. And we specify begin and end. These are names you choose. It should be of this type. And this is exactly what we have seen before in terms of code. No specific change happens. But with this approach, we can use our min function to vector like before, to double-ended queue, because this provides random access, which is an output iterator. List is bidirectional. It's more powerful than an output iterator. Therefore, our function template will work with list. And you can see with one function, we can perform polymorphic things, work with vectors, double-ended queues, lists, and any container providing output iterator. In order to perform operations or like printing data or reading data from constant containers, if they are constant, as I said, if the declare is constant, then the iterators shouldn't be able to modify the elements. Therefore, the C++ committee has introduced this constant iterator that does not allow changing data. You can dereference with that iterator, but just to copy values from there, not change values there. So constant containers are in this way available for various tasks. Like in this example, we have a constant vector passed to this maximum. What we want was to get the largest value in the vector. Therefore, we have no business on changing the element. And in order to work on this constant, we have to declare our iterator of this type, set it to that value, and then max value to 0, which is not the best approach, and then go till the end of the iterator, compare what it was read with the maximum so far, and if the current value is larger, we set the maximum value by copying and move to the next location and return what we get after we finish the while loop. Now, I said that it's not a good idea to set it to 0. this vector can have negative values, all negative. So I can have a constant vector with -3, -5, -9. Maximum value is -3, not 0. What is a small change you have to do? Set this to the first element in the sequence, dereference IT. Dereference IT, set the maximum value to the first element. And in this way, then you compare with every element and you end up with a proper maximum value. This works only if you have positive values in your vector. But be aware, this method, which is many times presented in books and stuff, does not work if you have this kind of vector. It gives you definitely the wrong answer if you have this vector, -5, -3, -9, -1. The maximum would be -1. Setting max value to this dereference IT and then do it like this, it's okay. And it will give you the correct value. Right. But you have seen an example of how to use constant iterator and why they are needed. And you have to be aware that it's a difference between constant iterator and an iterator which is constant. Things become more exciting, right, by combining things. So with a constant iterator, the code promises not to change the element to which it looks. This is not allowed. But you can change the iterator itself because you move through the elements. It's constant because it doesn't change the element in the container. With an iterator which is constant, you are not allowed to move through the container. You are stuck to some location, the beginning, but you are not allowed to move the iterator itself. You are allowed to change the elements in the container. Right, so this was just an interesting thing to be aware of. Now, when we talked about for loops, for ranges, probably you remember, it is a very good for loop to use when you have to work with a whole set. In that case, you can use a variable to access the whole set, being it a C-array, a vector, and any container. Double-ended queue is also good to work in this way. You can have a double-ended queue here. And you don't worry about going outside the array, because with this notation for ranges, you start at the beginning of the container and you end at the last significant element, because iterators are behind. Now be aware that with this notation, you introduce a variable in this scope. I, it's a variable which is matching each element in the array, not the index, element itself. And because it's a new variable, you can pass it by value or by reference. If you pass it by value, any changes which are here are not available outside the for loop, to be aware. If you pass it by reference, like here, any changes you do to your elements are available outside for loop. So with the first for loop, we set up the values in array, and those values stay there. Now, the same code apply for vectors and for double-ended queue, as I said, and for lists somewhere. You can use it. Now, you can think that behind this type of for loop is something like this iterator. This is not proper code. It's not proper code. It's something like this. It's a little bit more complicated. An iterator which sets I to the beginning of our vector and goes till the last element, with comparing. If begin is not end, we move to the next one. Okay? And we do something. I gets the value to which the current iterator points to. So be aware, this goes behind the scene, and if a data structure does not have corresponding items to an iterator pointer, then you can't apply for. C arrays, pointers in C are the most primitive type of iterators, and all type of containers are available. And here is a full program. We include vector. First, we construct the vector element with I times 5. So we get this element. Access by constant reference, not for integers, because you don't gain much. Better to just have int for your integer elements, but this is equivalent to this notation. Okay, so we just display what we had there. And now notice that now I is a reference to an int. We assume that we don't know what are the type of elements in V. If you don't know the types, you can use auto, and the system will know what is there. And notice that here, we change the value of elements in the array. Plus plus I means each element in V is changed and displayed. So we are here. After we go out of the for loop, we are here. And notice that the changes have preserved. Right. If you don't take this, you take the reference out from here. If you take the reference out, what you get with this is these values, but with this one, you get again 0, 5, up to 25. So you have to be aware a little bit about this. And this happens in Python as well. So we have seen that STL provides a hierarchy of iterators, and they are input iterators, out. Which other iterators are there? Bidirectional, forward, random. These are the 5 groups. And then various iterator classes implemented by containers have some characteristics as specified, operators specified by these categories. It's a good fact that we can write functions working on iterators, and that they will be applicable to many, many diverse types. So 45 minutes probably. We are not really having too much time. I have put this example on your stream, so you can work with that. And I combine more things. Now, as you can see, type name iterator is here. I can put a different value, just make it shorter. Right, so be aware this is what we choose. And I can put here A and B instead of it and N, but it's helping our understanding. And this is the function computing the min, and then we apply that function to various types. Notice that here we construct a C array and work with a C pointer like you work with iterators. I want to have this here to compare with approach with iterators, right here and here. So notice they are very similar. Then we construct a vector using pushback. We can construct a vector from this array, but I wanted to practice with methods in vector, and we get the same thing. And then construct a double-ended queue by pushing to front, and construct a list with different values, as you can see. And our templated function, which computes the min, is invoked for these three different types. This is an approach which is done by the STL algorithm themselves. Notice that the algorithm is not depending on the fact that it works on a vector or on a list or of something. The algorithm depends on what operators iterators provide, nothing else. So algorithms are designed like this, not linked to a container. The only thing you have to know about when you apply this algorithm is what operations the iterator have to provide. Dereferencing, moving to the next, and comparison. You have to be able to compare that you are pointing to the same. So these three operations, which are provided by most iterators, and then you can apply it to different containers. As you can see, we begin, it's an iterator provided by the vector, v end, the same thing. So this is the first part, and the second part refers to working with input and output iterators, which I talked about last lecture. But if we point it, disable the last part, as you can see, C-type array, C++ vector, they have exactly the same values because we use the same number. And then for the vector, the average sum divided by how many is 0.4, 4.5, which is what you expect. For double-ended queue, I divided by 10, so you get 0.5. And for the list, I multiply by 10 each element, therefore the average would be 45. But once again, it is a simple example to show you how STL is organized. Algorithms are defined separately, containers separately, and they interact via iterators. What iterators are provided by what type of operations are provided by iterators in container dictate whether an algorithm works or not on that container. So we stop here and you can change that and try